Hi, and welcome to module number 42. This module is going to be covering wavelets. Wavelets are a large area with a lot of research. One reference for those of you who are more interested would be a textbook by Stefan Mallat, which is called The Wavelet Tour of Signal Processing. And another option, my colleague Mike Waken has sent me his course notes, which are many dozens of slides, and I'll be happy to share them with people. So with that in mind, let's get started. The main idea in wavelets, so this is a multi-scale tool for time frequency analysis. So recall that the Fourier analysis lets you look at frequencies, and there's a duality between frequency and time. But wavelets are saying that sometimes you have portions of the signal in time where the signal has a lot of action, and there are other portions of the signal where it has less action. And for example, taking things to the extreme, a signal may be very smooth in a large area, but then another area be very jagged with discontinuities. And Fourier is not well suited for that. In contrast, what wavelets do, they allow you to look at the frequency content in different temporal areas. Or if you're looking at a spatial signal in perhaps 2D or 3D, different spatial areas. So wavelet structure exists at different scales. There's fine scale, fine details, and coarse scale, coarse, low level of details. At the fine scale, think about edges or tiny leaves in a tree that you're looking at in a picture. These are high frequency types of information, but their time duration or spatial duration is relatively short. On the other hand, at coarse scale, we have things that are large. They occupy a lot of time, a lot of space, but they appear at lower frequencies. So what wavelets do, they allow us, not in all cases, subject to some technical conditions, they allow us to construct an orthonormal basis. And overall, wavelets provide a sparse representation for varieties of piecewise smooth signals. So let's begin with continuous time wavelets. We're going to have a continuous time function psi of t. So psi of t is the wavelet. That is the definition, okay? The wavelet psi of t. And it's zero mean, and because it's continuous time, zero mean would implies that when we integrate over t, we integrate over psi of t dt, we get zero. But it also has unit norm, meaning that the squared magnitude of psi of t, when we integrate it, goes to 1. So again, we refer to psi of t as a wavelet, and it's typically concentrated around t equals 0. So typically, if the horizontal axis is t and the vertical axis is psi of t, typically a wavelet will look something like that and not something like that. So you'll note that in my second sketch, psi tilde of t, a big chunk of the action in the wavelet is happening over here, which is located away from 0. All right. So we have a definition for wavelets, and let's look at an example. This is called a Mexican hat wavelet. It's a second derivative of a Gaussian. So recall that if you have a Gaussian type of distribution, the horizontal axis would be t, and f of t for Gaussian distribution, or maybe fg of t, g for Gaussian, would look like that. And then when we look at the f prime of t, the derivative, initially it's positive but very small. Then over here in this region, it's positive but large. So here, positive but large, 0, negative and large, and gradually decays. So that's the first derivative. And the second derivative takes us to this form that we have in these two areas. We have a slightly negative derivative. At the peak, the second derivative is quite positive because we begin by being over here and we go way down, and Actually, now that I think about it, this is negative psi of t. So you need to flip it, okay? So this is the negative wavelength. So you have a steep change in the slope around t equals 0. And again, we taper off for large t. So why is it called a Mexican hat wavelet? Because if you take this thing and you rotate it, a rotated version looks like a Mexican hat. So a bit more about the continuous wavelet transform. Consider all possible translations to the left and right by you. And by the way, that's the parrot attempting to be a woodpecker. And imagine that the scale, which tells us whether you're coarse or fine, is a positive real number. So we define psi as a function of u, the translation, and s, the scale. Again, psi is not just a function of these two parameters, but also a function of t. It's 1 over square root of s, psi of t minus u divided by s. So let's think about this step by step. So first of all, the u, by subtracting u, it means that this wavelet is going to be centered around u. So that explains the translation. The scale means that dividing by s changes the density of the wavelet, how quickly it moves, and the normalization by 1 over square root of s ensures that we still have unit norm. So with this definition in mind, we can define a continuous wavelet transform for functions f that are in L2 of R. So in the course, we've often talked about an L2 norm, which means that if I have a discrete time signal x, the L2 norm is a summation over the elements, x of n squared magnitude, again, summation over n, and we're taking square root of this thing. Now, we say that x is a signal in L2. That means that x of n, this discrete time signal, its L2 norm is strictly finite. And now if x of t is in capital L2 over the real valued, over the real values means that t, the time domain, is real valued. That means that the L2 norm is finite. But what does it mean, the L2 norm, for a continuous time signal? That means that the integration over, let's say, t prime, going from negative infinity to plus infinity, f of t squared magnitude dt is finite. Okay, so finite energy signal. For a finite energy signal, or you could call it a function, the wavelet transform is denoted by wf as a function of u of s, and it's an inner product between the function f and the translated scaled wavelet psi us that we defined earlier. And this inner product, again, is an integral over f of t psi us of t conjugate. Now, comment about conjugates. If f is a real valued function and if psi is a real valued wavelet, the conjugate doesn't matter. So the conjugation only matters for complex valued things, right? And if you take home 1 point from this slide, I'm saying that we defined a wavelet, and now from the wavelet, we've extended our understanding to translations and scales. We have an entire transform, and this transform provides insights about time frequency behavior. What sort of insights? So let's look at an example. All right. So in our example, the top panel is a signal. The horizontal axis denotes the time t, and the vertical axis denotes the amplitude f of t. Again, you can call this a continuous time signal, you can call this a function, whatever you prefer. That's the top panel. And the lower panel represents the wavelet transform. The shades of gray that are kind of neutral gray means small, close to zero. The larger magnitudes are either dark grays and blacks, and also light grays and whites. So for example, in this region, we have large whites, and it could be that whites are positive and blacks are negative, whatever the signs are, negative, positive, positive, negative, whatever. And in this region, we have the dark grays and blacks, and again, large coefficients, but with a flipped sign. So let's now try to interpret these two things. So first of all, the vertical axis is the scale, and the horizontal axis is the translation, and there's a one-to-one correspondence between T and U, okay? So let's look at areas that are smooth, and suddenly there's a discontinuity. This discontinuity creates energy in the wavelet domain at the finer scales. So these are finer scales. And at the finer scales, what happens is that this discontinuity, it only has an impact right around, very near that location. And as we move down, the width of this thing becomes wider. And oftentimes people talk about a cone of influence. So the cone of influence is becoming wider as you move to coarser scale, all right? Now, another thing that I'd like you to note is that, again, in this smooth region, there's nothing. These are kind of medium grays. And here, whereas there's this second derivative, the bend in the graph, if you will, there's just a faint amount of energy. And again, these discontinuities create energy. So the left part of the signal is for the most part smooth with a few discontinuities, and the right part of the signal is very jagged. Because it's very jagged, here we have energy all over. So the key point here is that the large coefficients tend to be clustered around the discontinuity, and the coefficients decay in the smooth regions. This area here, as I was highlighting earlier, very little energy. So that's the insights both in the spatial domain and the frequency domain that wavelets can provide. Now, some more conditions, given some more technical conditions, the continuous transform is actually invertible. It can be shown that f of t is equal to this double integral, which on the one hand is looking at WF. WF are the actual wavelets, or the wavelet coefficients. And what we have over here, the psi, is the translated scale wavelet itself. So coefficients and wavelets. And if you think about it, this may remind you how in Fourier space, we're taking an integral over the coefficients multiplied by the sinusoids, where sinusoids, exponents depend on what type of Fourier expansion you're looking at. Now, of course, there's some type of normalization constant. You often have that when you're looking at wavelets. And another point to remember is that because the scale has this awkward type of relationship where at the coarse scales, the information changes very slowly, and at the finer scales, the information changes quickly, there's this division by s squared. So that's a fine point that you need to consider. But again, this is subject to some technical conditions. Now you can imagine that just like the Fourier transform has energy preserving properties, the continuous wavelet transform also has energy preserving properties. But now you may, after these details, you may be asking yourself, look, putting aside, yeah, you haven't told us about the technical details, but at a high level, can you at least explain why does it work? So at this point, hopefully you understand that around the discontinuities, there's information at a variety of scales, and in smooth areas of the signal, there's primarily information at the coarse scales, but why? So the idea is that the wavelet resembles a bandpass filter. Recall that a bandpass filter, if the horizontal axis is frequency omega, and the vertical axis is the magnitude of h of omega, a bandpass filter has this type of profile, that around the DC frequency 0, the response is low, close to 0, and at higher frequencies, again, the response is low, and it has two bands, all right? Now, the integral over psi of t dt is actually equal to h at frequency omega equal to 0. So this is the DC response. Now, I might need some normalization constant, like a 1 over 2 or 1 over square root of 2 pi or whatever. But at a high level, this is the DC constant. So we have no DC information, and therefore many of the band passes up to some normalization can be considered to be wavelets. So in our Mexican hat example, in the Fourier domain, the Mexican hat wavelet has this form, basically similar to two Gaussians, and the combination of two Gaussians is a bandpass, because at the lower frequencies around 0, there's no information, and at the higher frequencies, again, the frequency response decays. So different scales are going to correspond to different frequency bands, and what we're going to do, we're going to sample this bandpass filter's output at a rate that is proportional to the bandwidth. So consider both coarse scales first and then fine scales. At coarse scales, we have this bandpass filter, and at coarse scale, it means that we're applying it in a very slow way to low frequencies. So the bandpass filter is going to have a small bandwidth, and because of that, we'll sample slowly. Now, at a finer scale, what we're going to do, we're going to be considering higher frequencies. So let's kind of sketch that. At the coarse, let's call it C, we'll have this bandpass, and medium, which will be M. Let me try to do the coarse a bit more symmetric. At the medium, we may have this type of profile. And I'd like you to pay attention that my amplitudes are different because the medium has become wider. And what about the fine scale? The fine scale, this is frequency, so it has a lot of bandwidth, but it's also low. So it has this very wide profile, but a low amplitude. Now, what about sampling quickly? So if we're covering a lot of bandwidth with this fine scale wavelet, that means that there's a lot of detail in the time domain and we need to sample quickly. Okay, so we've talked about the wavelet transform. We've talked about inverting it, but what about the following challenge? The continuous wavelet transform, it's kind of similar to an orthogonal expansion because things have unit energy, and if you look at different scales and so on, you're going to have things that are somewhat orthogonal, perhaps not exactly orthogonal, but again, they're not exactly orthogonal, and because of that, if you look at all the possible wavelets together, all the S's and all the U's, it's going to be very redundant, highly redundant. So that challenge can be addressed by sampling a continuous transform to obtain a frame. So what I mean to say is as follows. Let's take the horizontal axis will be the translations U, and the vertical axis will be the scale S. And we're going to see this in the next slide, that at fine scales and coarse scales, as we discussed in the previous slide, we sample at a different rate. Okay, so at coarse scales, we sample slowly. And at fine scales, we sample a lot. Now, getting this frame, and again, it's a frame, it's not orthonormal, okay? Getting this frame requires quite a few technical details. So the devil is in the details. And some of the requirements of this guy are that we need to sample the scale in an exponential way, not in a linear way, but rather perhaps every factor of 2 increase in scale. Just in that case, this A constant would be a factor of 2. Now, at each scale, we're going to sample the translations uniformly, and the resolution needs to be proportional to the scale. So psi j n of t, j of n are now going to be integers. The j manifests itself in the scale. So the scale relates to j. And the translation is related to n. Now, just as a matter of definition, A1 is positive, and this constant U0 is also positive. Or actually, A is greater than 1. All right, so again, you could imagine this conceptually as A is equal to 2, but really, you could do this for different A's. And for those who are interested in details, the course notes by Mike Waken that you can email me about, I'll be glad to send over, and they contain many of these details. So as an illustration, what we're doing here, similar to what I sketched, the horizontal axis is going to be time, the vertical axis is going to be frequency. Here it's called omega, and at the coarse scale, or rather the coarse scale is below. At coarse scale, we are sampling slowly. So this is a long time, slow sampling. Let me actually type this up. So at the coarse scale, we sample slowly, lots of time between samples, but the frequencies are small. So it's a small frequency range. And because it's a small frequency range, it's a wide box, but a short box. So this is the frequency range. Now, what about the fine scales? So at fine scales, we're covering a lot of frequencies, a tall box, but it's also a thin box. So we need to sample frequently. And each of these points corresponds to a sample. And you can see that at the finer scale, we sample a lot. And at this medium scale, we sample in the middle. And you'll note how, indeed here, the ratio is 2 to 1. So these points are at the same time. These points are at the same time. These points, but I skipped this one and this one. So 2 to 1. And then at the next scale, I am, again, skipping half of the points at this interim scale. All right. So that'll be it about wavelets. We'll continue next time.